Welcome, everybody. Thank you all for coming. Today we have Sally Ng as a presenter for our seminar series. Sally Ng is a Baldwin Junior Faculty Fellow and an Assistant Professor in the School of Chemical and Biomolecular Engineering and the School of Earth and Atmospheric Sciences at the Georgia Institute of Technology. She received her doctorate in chemical engineering from the California Institute of Technology in 2007. And prior to joining Georgia Tech in 2011, she was a postdoctoral scholar and subsequently a senior researcher at Aerodyne Research. Dr. Ng's research focuses on fundamental understanding of the underlying chemical mechanisms of aerosol formation and composition, as well as the health effects of aerosols. Her group uses a synergistic approach in studying aerosols by performing both laboratory chamber experiments and ambient field measurements using advanced mass spectrometry technologies. She serves as a co-editor of Atmospheric Chemistry and Physics, as well as the Atmospheric Aerosol Working Group Chair and Publications Committee member for the American Association for Aerosol Research, AAAR, and as a director for the American Institute of Chemical Engineers. She's received the Sheldon Friedland Award, the Environmental Protection Agency Early Career Award, the Health Effects Institute Walter Rosenbluth's New Investigator Award, and the National Science Foundation Career Award. And with this, I would like to welcome you, and we're all excited to hear your talk.
Yep. Thanks so much for the introduction and for having me coming out to talk about some of the work we do. So it's been a really great visit. I got to see a lot of the facilities and meet a lot of people. And this morning, I got to see the RAF, which is amazing. I got to see the C-130 and G5 after reading so many papers about it. So thanks again. And so today, I'm going to talk about organic aerosols in the Southeast US. So I came from Atlanta. And the topic I'm going to focus is on nitrate radical oxidation of biogenic VOCs. And for those of you who have been to Atlanta, this is a picture of Atlanta. So we are literally a city in a forest. And this makes it an ideal place to look at the interaction between biogenic VOCs and also anthropogenic pollutant. So to this crowd, probably there's not too much introduction that is needed. So organic aerosols is everywhere. This is a figure from Jose's paper in 2009, which shows the submicron PM1 measured by AMS. And the green part of the pie is organics. And you can see that it is everywhere. On average, it accounts for about 50% of the fine PM mass all around the world. And they all look pretty oxidized. So just some of the basics, if you think of organic aerosols, you can broadly categorize them into primary and secondary. So for the primary aerosols, basically they're pretty much directly emitted. And at the same time, these different sources can also emit volatile organic compounds. And because our atmosphere is really oxidizing, so once these compounds get oxidized in the atmosphere, you made all these products of different volatility. So for the volatile products, they tend to stay in the gas phase. But if you're a little bit of semi-volatile or non-volatile, you actually want to be in the particle phase. And you can undergo gas particle partitioning to form SOA, or you can just nucleate and form new particles. And this is kind of the basic fundamental picture of the gas particle partitioning. And of course, in the last 10 years or so, we are learning that there's a lot more chemistry that can happen. You can have further oxidation in the gas phase. You can have heterogeneous aging or multi-phase chemistry and so on and so forth. So the way we look at this problem is that we try to do both fundamental studies and also ambient measurements. So I've been focusing mostly on ground measurements. I've never done any flight campaigns. So for the lab studies, on one hand, you can actually study a system in very great detail. So you can understand the fundamental mechanisms of how things actually evolve over time. And you can do isolated experiments. But at the same time, you've got to go to the field measurement and look at ambient aerosols evolution. So on one hand, you can use the data from the lab to help interpret ambient data, which is more complex. But once you go to the field, you can actually come back to the lab and you can do better experiments because now your experiments is actually more relevant to the atmosphere. And we use aerosol mass spectrometry techniques most of the case. So I was thinking before I go talk about nitrate radicals, maybe I'll give you a slide on what kind of projects that we are currently working on as a group. So of course, in the last couple of years, we spent a lot of effort to look at the effect of anthropogenic pollution on biogenic aerosol formation. So we look at the effect of sulfate and effect of NOx. So the effect of NOx is something that I'll talk about today in the talk. But for the sulfate, we find that it actually plays a critical part in isoprene aerosol formation, and that like a certain amount decrease in sulfate can actually lead to a reduction in isoprene aerosol. And one thing I'm really interested in is also linking peroxyradical chemistry and gas phase chemistry to aerosol formation. So I always think that you're what you eat. So when you think about aerosol composition and aerosol properties, we cannot forget about the fundamental gas phase mechanism, especially what happens to the peroxyradical. So depending on the reaction pathways of the peroxyradical, you make different products in the gas phase. So you end up getting different products in the aerosol phase. So recently we developed a technique to measure HO2 directly using SIM. So this is a paper we just published in AMTD. And so I've been in Denver for a couple of days in the last couple of days to attend the Health Effects Institute meeting. So part of my research group, we also work on the health effects of aerosol. So for this particular project, we are looking at intracellular ROS, which is reactive oxygen species generation in these cells. And we are developing cellular assays and exposing them to different pollutants that we collect from the ambient or produce in the chambers. And of course, different type of aerosol will result in different toxicity. And last but not least, I recently started a project to look at the effect of vapor wall loss, because the chamber facility that I built at Georgia Tech was fairly new. So I was interested in characterizing the vapor wall loss in the chamber facility that's about 13 cubic meters, and understand how these wall loss can affect aerosol formation. So this is just kind of what we have been doing recently. And of course, today I'm going to focus on the nitrate radical oxidation. And if you are interested in more of these other projects, I'll be happy to talk to you after the seminar. So the underlying theme is that there seems to be this interaction between biogenic and anthropogenic emission. So we know that there's a lot of SOA, but how much of it is actually from anthropogenic sources, and how much of it is actually from biogenic sources? Or maybe there's no clear cut in saying what is what, because there's this interaction between them. And this is a paper from my colleague, Ronnie Weber, back in 2007. So basically what they did is that they saw that based on C14 analysis, a lot of the carbon is biogenic. But at the same time, WSOC, which is the water-soluble organic carbon, correlates really nicely with CO, which is an anthropogenic pollutant. So the question is there some sort of interaction happening between this anthropogenic pollution and biogenic aerosol formation? And that's kind of the question of what is the mechanism, and how much is this anthropogenic influence on biogenic aerosol formation? So why nitrate radicals? So I've been interested in nitrate radicals since 2007, but I stopped doing that for a while. And nitrate radical is a major nighttime oxidant. And previous studies have shown that the aerosol formation potential of nitrate radical and BVOC is actually very high. But if you look into the literature, most of the aerosol study is focusing on daytime chemistry, on ozonolysis. So relatively speaking, this is kind of a fairly understudied topic. And nitrate radical is formed from NO2 and ozone, which is an anthropogenic pollutant. So if you think about the reaction of nitrate radicals and biogenic VOCs, then that provides a mechanism for linking anthropogenic pollutions and biogenic aerosol formation. So I'll start with the ambient measurements. So this is the two big campaigns that my group participated in the last couple years. So I'm sure many of you are familiar with SOAS. So we were at the ground site at Centreville here in 2013. And we also participate in a big measurement campaign at Georgia Tech. So we have an EPA health center to look at the health effects of aerosols. And my portion of the project was to go around and measure all this aerosol composition around Atlanta. So we did multiple measurements at different sites in the greater Atlanta area. So we have this pair of sites, which is operated by the Surge Network at Jefferson Street, at Yorkville, which is a rural site. And we have a site on top of our building, on the roof of our building. And this is a roadside site directly next to the I-75 and 85. So basically, we moved the aerosol mass spectrometer around all these sites in a couple years of time frame. And this is a picture of the SOAS, which probably many of you are familiar with. So this is our trailer. This is my student, Lusu, happily working with the AMS. And we were there for a month and a half. And so because Georgia Tech, we have a lot of people at SOAS. So my colleague Ronnie Weber and Thanos Nennis and their students are also at SOAS. So the Georgia Tech communications sent a reporter here and wrote a story about us spending 6 weeks in the forest. So this is a schematic of the high-resolution AMS, which again is probably very familiar to all of you. And it just provides continuous measurement of organics, nitrate, sulfate, chloride, and ammonium. So when I first moved to Aerodyne as a postdoc, the first thing I learned is the color scheme. You gotta get the colors right. If not, that word snob is going to chase you after the hallway. So, because it's a high-resolution instrument, so we can actually do elemental analysis. So you can get the O to C ratio and H to C ratio of these aerosol composition. And because it is a time-resolution, time-of-flight instrument, you can also get size-resolved composition. So these pie charts here basically shows the PM1 composition. So the way I'm going to frame these pie charts is that the ones on the top are going to be from summer data or warmer months. The ones that is at the bottom are going to be from winter. And these are the different sites. And if you just look at the PM1 loading, you can see that in Atlanta it's about 10, 15 microgram per cubic meter. And it is a little bit more in summer and maybe a little bit lower in winter. And if you remember the color code, the green is the organics. So again, we see that organics kind of dominant the submicron PM1, which is very similar to many parts of the world. And one thing about AMS is great. It sees everything. The drawback of AMS is that it's electron impact, so everything fragments. So in order to get some understanding of where your aerosols come from, that we try to do this positive matrix factorization. Basically, we put this whole mass spectral time series we acquire from a few measurements, and we do this analysis that allow us to tease out the different factors that could contribute to the overall aerosol contribution. And you can see the time series of these factors are also different. So I won't be able to talk about how we do this analysis for each data set, but this is data from SOAS, and I will use this as an illustration to show how this method works. So when you do the PMF analysis, these are the factors that we obtained for the SOAS data set. So we have the biomass burning organic aerosol, BVOA, which is typically have a signal at 60 and 73, which are fragments of levoglucosan. And the isoprene SOA also has a very unique signature at 53 and 82, which likely comes from the uptake of IEPOX. And then you got these two different types of aerosol, so we call them more oxidized or less oxidized oxygenated organic aerosol. And they're just separated based on the relative signal intensity at CO2, which is likely the fragmentation of carboxylic acid. So the higher the fragment at F44, then we call that the more oxygenated aerosol. And you can see that this is the diurnal trend of all these different factors, and they show very distinct trends during this campaign. And this is the mass fraction. So today with the 1 hour seminar, I'm going to focus on mostly this LOOA, which is the light green color of the pie. And you can see that it's about 30% of the total aerosol in Centreville. So if you look together at all these pie charts now, so this is organic aerosol for all the sites that we got data from. Again, this is the summer data, this is the winter data. So the couple of things that you learn from these pie charts immediately is that the organic aerosol source seems to vary seasonally and spatially at these different sites and different locations and seasons. And one thing you see that is I'm not going to talk too much about it, but for the isoprene SOA, which is the blue part of the pie, you see that it's only on top, which is the warmer months. So we can actually only see isoprene aerosol formation in the summer, which is actually consistent with its emission. But one thing is about this LOOA, the light green, you can see that it's everywhere, so it does not go away in winter. And we'll talk about where this comes from and what chemistry could potentially contribute to this factor. And you can see it accounts for quite a large fraction of the total ambient OA in the Southeast US. So we work with Chris Knott at NCAR, and I guess he's no longer here, but he did some spectrometry analysis for us for the SOAS data set. And we find that no matter where the AMS come from, we always see this peak at night. So this is from the northwest, you got the peak at night. From the northeast, you also see the peak at night. Maybe not so obvious in the southeast, but also pretty obvious in the southwest. So usually you don't really think about aerosol peaking at night, because if you think of photochemistry driving all the gas oxidation and gas particle partitioning, you think of an aerosol diurnal time series might peak during the day. So when we see this nighttime peak, the first question we want to make sure is whether it is locally produced or is actually from long-range transport. So these are the data. So the previous slide is the data from Centreville. So now these are all the diurnal trends of that LOOA factor from all these other sites and all other seasons. So what we see is that no matter where we sampled, which year or which season we sampled, we always see this nighttime peak. And this diurnal trend is pretty consistent regardless where we do our measurements. So it seems to us is that there's some sort of local production happening at all these sites, at all these seasons. But then one question you always get asked if you study atmospheric chemistry, like I teach the undergrads, they will be like, well, at night, the boundary layer is also shallower. So maybe the nighttime peak that we are seeing is just simply from the boundary layer height being shallower, and you have an enhanced concentration at night. So to look into that, we multiplied our concentration by the boundary layer height measured by the search folks. And what we see is that after we correct for the boundary layer height, there's also this increase at night. So these seems to be pointing to the direction there is some sort of chemistry that is leading this aerosol production at night that we end up measuring with our instrument. So what is this potential chemistry? So the figure here shows you the diurnal trend of this LOOA, which is the solid green. And the dotted lines are all VOC data measured by Joost de Gouw and Alan Goldstein. And so you can see that the isoprene, this one peaks during the day. And these two are the alpha-pinene and beta-pinene. And these are the most abundant monoterpenes at Centreville, and they peak at night. So isoprene emission is more dependent on the light. So that's why isoprene emission kind of goes away in the evening. But monoterpene emission is not so much as determined by light versus temperature. And so you still have this high monoterpene concentration at night. So what you see is that a couple pieces of observations. The LOOA has a nighttime peak. The monoterpenes also have a nighttime peak. And nitrate radical is a nighttime oxidant. So these seems to be suggesting these locally produced aerosols could be from the nitrate radical oxidation of monoterpenes, such as alpha-pinene and beta-pinene. So last piece of evidence here is that, so this time series is now the LOOA, and this is the organic nitrates. So if the SOA is formed mostly from BVOC plus nitrate radicals, you expect to see this SOA correlate with organic nitrates. And indeed, this is what we see here, that the LOOA actually is really strongly associated with organic nitrates in the particle phase. And so all together, we point to this contribution of monoterpene plus nitrate radical chemistry to LOOA. The question is, how do we actually calculate organic nitrates in the particle phase? So we don't really have a direct measurement of the particle phase organic nitrate concentration. So at SOAS, we were lucky that Ronnie Weber was also there, so he had a pulse. So one way we can actually look at is to take the difference between AMS, which measures the total nitrate, and pulse, which measures the inorganic nitrate. And for the other sites, we don't have the pulse running, so we have to resort to these two other methods to obtain the concentration of the organic nitrates, which I'll go into a little bit more detail in the next couple of slides. So just a word of caution about this method that we use just by taking the direct difference between the AMS and pulse. So you can see that at the beginning of the campaign, we forgot that the pulse and AMS actually have very different cut size. So pulse has a PM2.5 cyclone inlet and AMS is a PM1. And it's good that at the middle of the campaign we realized we should change the pulse inlet to PM1, so we are actually measuring the same thing. And this is not kind of at the beginning, this is not what we set out to do to measure organic nitrate, but halfway through the campaign we're like, this will be a nice method to obtain a more direct measurement of organic nitrate, so I convinced Ronnie to change the cyclone. And what we see here is that there could be potential complications of the nitrate in the pulse from mineral dust. So the good thing is that as soon as we change the pulse cyclone from PM2.5 to PM1, you can see that the sodium measured by the pulse is actually very negligible, so which supports that we can actually use the difference of the AMS and pulse IC to get a concentration of the organic nitrates. So for the other data sets all around Atlanta, we don't have the pulse kind of parading Atlanta with us for all these measurements. So we basically entirely relied on the AMS to obtain a quantitative measurement of the particulate organic nitrates. So this is a method that was proposed by Delphine in 2010. And basically, like the fragment or the contribution of the NO and NO2. So when you have a particle organic nitrate in the AMS, it will fragment to NO and NO2. And this is the formula that you can use to calculate how much of these concentrations are from each species. So the formula here, this R measured, is basically the NO-NO2 ratio in your mass spectra for the ambient aerosol. And this is the NO-NO2 ratio for ammonium nitrate, and typically it's about 2. And this one is the NO-NO2 ratio of organic nitrate, and it really depends on the VOC, and it also kind of depends on the instrument. And so this kind of complicates the use of this method to estimate particulate organic nitrate contribution. So we have to go through a lot of different calculations, and there's a lot of details here which I won't have time to go through, but we discussed that in Lu Su's ACP paper. So at the end of the day, we use an RON of 5 and 10 as our upper and lower bound to use this method. We call that the NOx method to estimate organic nitrate concentration. The question is, how well do we do using this method, right? And the good thing is, at SOAS, we sort of have the answer, because for SOAS, we actually have the AMS and POS. So in this scatter plot, what I'm plotting here, the y-axis is the nitrate group that is calculated by the difference between AMS and POS. And the x-axis is this NOx method using an RON ratio of 5 and 10. And as you can see, for RON values of 5 and 10, it kind of bound the measurements that we obtain by the more direct method of AMS and IC. And there's some differences in the slope. It's not quite 1, but it's pretty, plus minus 20, 30%. So without any more direct measurement, this is a pretty good, estimate in terms of the particle organic nitrate contribution. So the last method that we use is PMF. So at the very beginning of my talk, I was like, we run PMF analysis to figure out where the organic aerosols come from. And most of the time when we do PMF analysis, we just put organic mass spectra in there. So in this method, we actually put the nitrate back into PMF analysis, and we want to see where the nitrate goes. Does it go with the organic species, or does it form its own factor? And that's what we did with this PMF or plus nitrate methods. And we see different things for different sites. For some sites, the NO and NO2 will go with an organic factor. So that seems to signify that it's some sort of organic nitrate. But in some sites, we actually obtain a pretty pure inorganic nitrate. So in a sense, then we actually get a source apportionment of how much nitrate is actually organic and how much nitrate is inorganic. So these are kind of the 3 different methods that allow us to obtain a measurement or some sort of an idea of what is the particulate organic nitrate concentration. So when we put all these together, this is what we find. So this is the concentration of the nitrate groups. These are the different sites and different seasons. So this red dots here now shows all the measured, the total nitrate. And the green ones here shows the contribution that is of organic origin. So it's pretty constant, about maybe 0.2 microgram per cubic meter. And if you look at the inorganic one, you can see that the concentration is fairly similar here in summer months, and then in winter, the inorganic nitrate goes up, which is not surprising because the temperature is lower in winter, and so you have more inorganic nitrate partitioning into your particle phase. And if we look into this in terms of the fraction of how much nitrate is organic versus how much is inorganic, this is what we get. So on average, you get about 63 to 100% of the nitrates that we measured organic in origin. And remember, this is just the nitrate group. So if you have an organic nitrate, you got the organics part and the nitrate group sticking out. So in order to calculate what is the total mass of the organic nitrate, you got to assume a molecular weight. Or somebody will have to go and measure these molecules more directly. And so we assume a molecular weight of 200 and 300, and on average we get about 12% or up to 12% in summer of the total organic aerosol is in nitrate form. So that's kind of where we ended with the few campaigns. We learned that the organic nitrate is an important component of aerosols. We learned that monoterpenes plus nitrate radicals seems to be contributing to all these aerosol formation. But I got my training in more of a fundamental experiment. So I was like, okay, can we actually quantify how much the monoterpene nitrate radical is contributing to ambient aerosol? So to answer that question, I have to go back to the lab and do some fundamental lab studies. So we try to replicate the ambient conditions in SOAS in our chamber. So what are those? So if you've been to Atlanta or if you're at SOAS, you know that it's really hot and humid. So we try to make sure that we do experiments at high humidity that is more relevant of the ambient condition. And this paper led by Rodney Weber's group showed that the aerosol in the southeast is really acidic. It's about pH 1. So we make sure that we also use acidic particles in our experiments. And as you saw at the beginning of the talk, the aerosol loading is about 10 microgram per cubic meter. And one thing that we also systematically look into is what is the fate of the peroxy radicals in these experiments. And the top 3 VOC monoterpenes that we look at is alpha-pinene, beta-pinene, and limonene. And another thing that we are very interested in is what happens to all these aerosols and organic nitrates after they are formed. So I was talking to Elmer earlier today, in the models or in experiments, we always do photooxidation experiments, so you got eternal sunshine, or you do dark experiments, so you got eternal darkness. But if you're an aerosol particle, you have a lifetime of about a week. So I see 6 nights and 6 days, right? So this change between night and day has never really been studied before, even though we know that in the real world, aerosol actually experience this kind of perturbation. So I'm interested in seeing what happens between night and day. In the mornings, when the temperature increases, when there might be dilution because of the boundary layer, and also, there's photooxidation, when the sun comes out. So what happened to these aerosol and organic nitrates when you actually look into this night-to-day transition? So just a couple words about the peroxy radical chemistry. So as I mentioned earlier, this is really the centerpiece of what happened or what is formed in the gas phase. So depending on which reaction pathways that you take, you make this all different products in the gas phase. And if they partition into aerosol, your aerosol composition will also be completely different. So for this set of experiment, we are focusing on the HO2 channel and also the RO2 plus NO3 channel. And this is kind of a cartoon showing what I meant by this night-to-day transition, that you make all these aerosols during the day, you get a night, and then you see this night-to-day transition. And that's why we're trying to do experiments in the chamber to look at the effects of these different perturbations and see what happened to the aerosol. So the reason why I started with field campaign data, and there is a reason for that. So I showed up at Georgia Tech in 2011, and I want to do chamber experiments because I have done a lot of ambient measurements when I was at Aerodyne. And it took me 2 years to build a chamber. So basically, the good thing is that those 2 years I actually end up doing a lot of ambient measurements that I just talked about. So when I'm ready to do the chamber experiments, and this is kind of where I started with, and this is the little hand drawing that I had when I showed up at Georgia Tech in August 2011. And so I got these 2 rooms, which is very nice. This is actually Thanos Lennis' lab, and he let me use maybe 5 feet of his lab so I can actually put a table here for injection. And this is basically a schematic of the chamber enclosure. This is the 2 chamber and facilities that I thought about maybe 10 cubic meters. And so I was kind of there doing all these measurements. And they take a year, and then we get to this stage. So we got the frame, and this is what it looks inside. This is what it looks, outside. And I was telling, Christine earlier that it was pretty challenging because at the beginning I'm like 1 person, and I got 1 student, so it's like 2 of us, and we're undertaking this big effort. But it's all worth it. So in 2013, we finally get it built. And this is my first 2 students, Chris and Lou, and we were putting up the chamber. And so the chamber has 4 corners, so we got 3 people. So I have to recruit my husband to help me put up the chamber for the 4 corner. Yeah, but this is really nice and shiny, and now we can actually go back and do all the fundamental studies that I would love to do. So this is the nicer schematic. So you can see that we got 2 13 cubic meter bags, and surrounding the facility, we got all these amazing nice instruments that allow us to characterize the gas phase and particle phase composition. So I do a lot of real-time measurements. So all these instruments are connected to the chamber. And one thing I spend a lot of time is that I try to make sure that we have a wider temperature range so we can actually do more experiments under different conditions. And it was really challenging to get the chamber facility down to a couple degrees Celsius, because when you have 300 UV lights, you turn them on, it's kind of a chemical engineering heat transfer problem to how to get away all the heat in a very short time. And so this is kind of a list of the instrumentation that we have in the chamber facility. So at the, Greg Huey was there, so he has a lot of SIMs, so he was very nice to let us borrow his SIMs to do some measurements. And last 2 years, we got a NSF MRI proposal funded, so we were able to buy a high-resolution time-of-flight SIMs, which is really great. And we also got the Figaro inlet, so we can do aerosol and particle speciated measurements in real time. And of course, we got the high resolution time of flight AMS. And so this is kind of aerosol growth as a function of time for the alpha-pinene and beta-pinene experiments. So alpha-pinene and beta-pinene, they look very similar structure-wise, but they have very different aerosol formation potential when it comes to nitrate radical chemistry. So for this experiment, they're done under exactly the same condition. We put in 12 ppb of alpha-pinene in one reactor, 12 ppb of beta-pinene in another reactor. And you can see that as time goes by and reaction happens, you make SOA, and this dotted line is beta-pinene, this solid line is alpha-pinene. So you make way more aerosol from beta-pinene oxidation than alpha-pinene. And alpha-pinene, we see a little bit of aerosol. It's not entirely zero, but tiny bit. And so the SOAU is pretty low, about 4.3%. And for limonene is a very powerhouse for making aerosol. So we did experiments at both two different temperatures. So this is the U curve, which is the aerosol formation potential, kind of, if you think of it as a amount of aerosol formed per amount of hydrocarbon reacted. And this is the aerosol loading. So this line is the aerosol form at 25 degrees Celsius. So it is horizontal. What it means is that the aerosol form under this condition is almost essentially non-volatile. And you can see the aerosol yield is 170%, which is a lot. So basically, you put in a tiny bit of limonene into the chamber, you make a lot of aerosol. And when we do experiments at 40 degrees Celsius, you started to see this more semi-volatile behavior. And if we look at the data between 40 and 25 and use the Clausius-Clapeyron equation, we can actually backtrack what is the enthalpy of vaporization. And what we find is that it's really highly dependent on the loading, and it could be as high as 160 kilojoule per mole. So it seems that this value has been varied quite a bit in the models, depending on which model you use. People might use different values. I'll talk to Devin later, maybe. So for the SOA yields, what we find is, so this is the data that we found from the RO2 plus NO3 pathway, so back to the peroxy radical reaction, and this is the RO2 plus HO2 pathway. So if you compare the yields for these two reaction channels, maybe the good news for the modelers is that the aerosol yield is actually very comparable. So maybe you don't need to worry about what your peroxy radical is reacting with, at least for this system. And the aerosol yield is actually quite high, like it's about, for 50 microgram per cubic meter, it's about 60%. So the aerosol formation is pretty high for beta-pinene. And we also did experiments at different humidities. So this data, like the open ones are the dry conditions, the solid ones are the humid conditions. And you can see that they actually kind of follow on the same U curve. So again, this seems to suggest that humidity does not really change, at least the overall mass yield. Maybe at the speciated level, they will change the composition quite a bit, but in terms of the overall aerosol mass that they made under these two different humid conditions, there didn't seem to be a big difference. And overall, you can get to about almost 100% of aerosol yield. So remember, back at the beginning, I talked about SOAS, in which the most abundant monoterpenes are alpha-pinene and beta-pinene, and limonene is a little bit. So alpha-pinene is the most abundant VOC, or monoterpene, but it does not have that much of an aerosol yield. And beta-pinene is the second most abundant biogenic VOC, and it has a very high SOA yield. So when you take into account of the aerosol yield and the VOC concentration, it seems that the beta-pinene plus NO3 can actually contribute to a lot of the LOOA that we are talking about at the beginning of the talk. So this figure shows some of the organic nitrate species measured by SIMS. And here is where the reaction starts. And as you can see, when reaction starts, we immediately form organic aerosol. And these different species, as measured, organic nitrates measured by the SIMS also go up pretty quickly. So the difference between nitrate radical reaction and maybe some of the photooxidation experiment is that the reaction rate is really fast. So you actually finish making your aerosol in a couple hours, which I'm sure a lot of students love that. So this is the proposed mechanism. You're going from beta-pinene, and you go through all these different steps to think about what are the species that you've measured. And these are kind of the organic nitrates that we measure, and these are the proposed chemical formula based on their mass to charge. And this is the vapor pressure estimated. So it seems that all these are really, non-volatile species. And for the purple ones are the ones that we see more under RO2 plus HO2 condition. And which makes sense because for the RO2 and HO2, you expect to make some peroxides. And in these, you can see that indeed they have some peroxide functional groups. So this allows us to kind of get a better sense of what is the chemical mechanism that leading to all these aerosol formation. So this is a typical aerosol mass spectra for the beta-pinene plus NO3. So if you're not used to AMS mass spectra, I'll just point you to the NO and NO2. Remember, I said, if you're an organic nitrate, you fragment to NO and NO2. And for this organic nitrate, the NO-NO2 ratio is about 5 to 10, depending on the type of experiment that we do. And overall, that the organic nitrate actually make up about 45 to 74% of the organic aerosol that we measured. And one thing I would also like to point to your attention is like we're very interested in what are these special features about this mass spectra sticking out at 67 and 91. So 91 is the C7H7 fragment. And usually you think of 91 as coming from aromatics. Like aromatics, when you fragment, you get a 91 signal. So this is very interesting that we keep seeing this in all the data that we see in the Southeast US, like where did this 91 fragment come from? And it seems that this could potentially also be associated with monoterpene aerosols. And we keep the experiment running by adding more N2O5 and NO3. And we think about aging as aerosol continue to be oxidized over a longer time scale. And the dark aging doesn't really seem to do much compared to probably the photochemical aging. We didn't see a huge change in O2C with dark aging. It's a little bit increased, but not too much. So if we compare the mass spectra of this beta-pinene with this LOOA at SOAS, they share some unique features in terms of the 67 and 91, and also the 43 and 44. And so kind of coming backwards, so we did all the ambient measurements, and then we come back to the lab to do all these fundamental studies to actually try to quantify how much aerosol can be formed from beta-pinene plus NO3. So kind of putting all this together to look at the SOAS data again, we find that for nighttime, that the NO3 oxidation of BVOCs actually account for 64%, and the rest react with ozone. And in terms of all the 64% of BVOC plus NO3, majority of it react with monoterpenes instead of isoprene and nite. And because, as I mentioned, that the monoterpenes, alpha-pinene does not have that much of an aerosol yield, so it's mostly with beta-pinenes. So what we find is that the beta-pinene plus NO3 oxidation can make up a large fraction of the LOOA, which is the green part of the pie that I mentioned at the beginning of the talk. So I will talk a couple words about the Figaro high-res SIMS. This is the new instrument that we acquired, and this is a paper by Joe Thornton's group. And this is a very nice instrument that allows us to look at the speciated composition in both the particle and gas phase. It's almost like a semi-continuous measurement. So you look at the composition by having a filter that moves on and off, and that you collect the aerosols on the filter, and then you thermally distort that collected aerosols. And we use I- as reagent ion. So at first we tried with acetate, but we see so many peaks with acetate ionization that was really hard to understand or interpret the data. So the I- actually give us a more clean mass spectra. And so we did these experiments with beta-pinene and also alpha-pinene, which I'll talk about later. So this is the composition of the particle phase organic nitrate that we measured in the beta-pinene experiment, and this is the corresponding gas phase species. So what you can see is that, so this is the C10, C9, C8, C7. So beta-pinene is a C10 monoterpene. And you see all these organic nitrates being formed, and they're really highly oxygenated. They have like up to 9 oxygen atoms. And the thing is that you don't need to wait for these to be formed, because when you think of a compound that has a lot of oxygen atoms, you take a long time, undergo aging and aging and aging until your O2C increases. But this is pretty formed immediately as soon as we start the reaction. And this is consistent with some of the papers that have been published earlier, proposing this octo-oxidation mechanism that allows you to form these highly oxygenated species in a first, very short time frame. So this table, I don't expect you to read all of them, but I just want to show that these are kind of the organic nitrate species that we were able to measure with the Figaro time-of-flight SIMS. And we observed 41 organic nitrates for the beta-pinene, and we observed only 5 organic nitrates for the alpha-pinene plus NO3. And Joe Thornton's group just published a paper earlier this year, and out of these 41, 32 have been observed as SOAS, and out of this 5, 4 of them have been observed as SOAS. So this is a nice, consistent story about all these organic nitrates could potentially be formed in an ambient environment where you have nitrate radicals and BVOCs. So come back to the earlier slide that I showed the day and night transition. So one thing that I'm very interested in is what happens to all these organic nitrates after they're made. Do they last forever? Do they deposit? Do they get chemically transformed? And so on and so forth. So this schematic kind of showing like all the different processes that can potentially happen. So you got this gas phase organic nitrate. You can undergo gas particle partitioning to form particle organic nitrate. And in the particle phase, if you have aqueous water, you can potentially hydrolyze and make nitric acid. Or all these gas phase and particle phase nitrate can also be photolyzed, or they can react with OH when the sun comes out in the next morning. And of course, there's the deposition, which is also highly, uncertain. And so we would like to do some experiments to kind of examine what happened, to these organic nitrates. So the first thing that we look at, number 1, is the hydrolysis. So remember, we have 2 chambers, so we can do dual experiments, dry experiment and humid experiment, with the same condition except the humidity. And this figure here, the y-axis is basically the nitrate to organic ratio in the wet experiment normalized by the dry experiment. So if everything equal, you should expect a horizontal line around 1, because everything's supposed to be the same. And what we find is that it decreases slowly, and then it kind of level off after like 300 minutes, and only about 10% of it actually decrease. So if we go back to look at the literature, and the mechanism that I show at the middle of the talk with all these chemical species, it seems that a lot of the organic nitrate that is being formed is primary. And based on previous studies, the primary organic nitrates do not hydrolyze at the fast rates. And maybe 10% of these are actually tertiary nitrates. And the hydrolysis lifetime here is about 3 to 4 hours, which is consistent with previous studies. So if you think about organic nitrate in the ambient, where could they come from? So today's talk, I'm very biased on the nighttime chemistry. But you think about the daytime, in the presence of NOx, photooxidation of BVOCs can also make organic nitrates. So are these organic nitrates made in the day and night equal, or they have the same property? So in terms of hydrolysis, so this is kind of what we find, and based on the previous slides, that a lot of these seems to be primary or secondary organic nitrates. But there's not that much study based on the photooxidation during the day. So this is a paper by Ali. And basically, they assume that most of the daytime organic nitrate is actually tertiary. So based on all these information, we need to be careful about what organic nitrates that we are talking about. For the primary and secondary, they don't hydrolyze very fast. But for the tertiary, they hydrolyze in the minutes and hours of lifetime. But the question is, maybe the nighttime chemistry and daytime chemistry mix different relative amount of different type of nitrate. So this is something that needs to be considered, maybe potentially in future modeling effort to try to look at what is the fate of organic nitrate. So this is the hydrolysis. So what about the night to day when you turn on the light so that you let the aerosol see the light of the day? So we make aerosol at night in the dark. So this is the beta-pinene, this is the alpha-pinene. And maybe I'll just focus on this figures here. So the black line is when we turn on the light. And this is the particulate organic nitrate. So you see that for beta-pinene, if I didn't really tell you when we turn on the light, probably you would not know when we turn on the light, because nothing seems to be really happened after we turn on the light. But for alpha-pinene, as soon as we turn on the light, we lose all the organic nitrate. So it seems that it completely gets photolyzed, or it reacts with OH and repartition back to the gas phase. And this is actually have important implications of what happened to all the NOx that is get trapped, as organic nitrate. So the third thing that would perturb the system is dilution, because as the morning comes, boundary layer increases, so we get more, diluted boundary layer with all these aerosols. So for this particular experiment, we actually plot the time since dilution begins. And you can see that nothing really happens after we dilute the aerosol with clean air in the chamber. So it seems that the dilution does not really allow all the maybe semi-volatile products, or maybe they are too non-volatile, that they would not even repartition back into the gas phase even when we dilute. So now what about the last one, temperature? When the morning comes, the temperature increases. So what happened to these organic nitrates and organic aerosols? So these are two different experiments, and this is basically the AMS organic to sulfate ratio, and you can think of it as a normalized aerosol mass. So let's look at this figure. So this is the aerosol formation at 40 degrees Celsius. You make a bunch of aerosol, and it's kind of stay constant over the experiment. And then we do another experiment. We do experiments at 25, and we make more aerosol because now the temperature is lower, so more of the semi-volatile species can partition. And at this particular moment, about 220 to 30 minutes, for this experiment, we heat it up. So you would think that maybe when we try to heat it up so we heat it up from 25 to 40, so you might expect that this will decrease all the way back down and match with what it is at the 40. But it seems it's not the case. It's like once we heat up the aerosol, it does decrease a little bit, maybe 20%, but after that, it's really kind of slow decrease, and really in the time scale of our experiments, never reach this level that is formed at the 40 degrees Celsius line. So this seems to imply that there's some sort of resistance to evaporation, and that maybe potentially aerosols can acquire these core shell structures in which the materials on the shell is inhibiting the materials in the core to react. So I won't have the time to talk about this in more detail, but we also actually do experiments with two different types of aerosol. We first form the beta-pinene aerosol in the chamber, and then we form 9 million aerosol to coat around it and see what happens. And even for this mixed system, we are seeing this kind of core shell structure. And this is something that we are still trying to learn more, but this could potentially have implications of depending on how your aerosol is formed. If they're not evaporating, as the temperature increases, maybe you change the dynamics and how much aerosol is after it's transported away from where it is made. So just kind of to wrap all this together, so I started with the field measurements because at that time I was still building my chamber. And so for the ambient measurements, we find that this LOA contribute a lot to the ambient aerosols in the Southeast US and by reacting with nitrate radicals. So this is kind of the NOx effects that I was referring to. And on average, the aerosol organic nitrates contribute about 12% of the ambient aerosols in the Southeast US. And for the beta-pinene+NO3, we systematically look at the effect of proxy radical and effect of humidity, but we didn't see much of strong effect of these two parameters on the aerosol formation. And with the use of high-res toxims, we were able to measure a lot of these speciated organic nitrates. And in the talk, I show you what happened to the total organic nitrate. But with all the 70 speciated organic nitrates that we measure, actually they have different evolutions when we turn on the light. So this is something that is potentially very interesting to try to understand what are these different types of organic nitrates and why are they behaving differently when we turn on the lights. And in terms of what happens to the organic nitrate with these different perturbations, the hydrolysis, it seems that a lot of the organic nitrate formed from the beta-pinene does not react, and they would just stay as organic nitrates no matter, even though we have high humidity. And that for the particular organic nitrates, when we turn on the lights, it seems that the aerosols formed from the organic nitrates formed from alpha-pinene and beta-pinene do very different things. So in a sense that when you think about the reaction of nitrate radical with BVOC is a way to kind of trap the NOx into an organic nitrate form, and whether this organic nitrate is released back to the atmosphere as NOx will potentially actually affect maybe the next day ozone production. If the beta-pinene nitrate does not really do anything, it does not get evaporated when we dilute it, it did not really hydrolyze, it did not get photolyzed, maybe the fate of these nitrates will be deposition. But for alpha-pinene, it seems that it will just release all that NOx back to the atmosphere the next day when the sun comes out. So this is an important question to kind of figure out, do the organic nitrates as a sum, do they serve as a NOx sink or NOx source? And what we find is that the temperature does not really seem to promote that much, even though it's still more than the dilution. And finally, there's this resistance to aerosol evaporation that potentially these aerosols we are making taking a core shell structure. And this is something that we'll look into more in the future. So just kind of to wrap up in a sense that I was talking to some of you during the meetings is that I started my research career in the lab doing very fundamental chamber studies. And I went to Aerodyne to learn how to do ground measurements. And in a sense that it made me appreciate fundamental studies much more. So last year I was here for the IGEC fundamentals workshop. And I do think that this is kind of my take-home point, that I always think that laboratory experiments should really be a nice integrated part of field studies. Because after we collected all these AMS data. At the end, I have to go back to my lab and do all these fundamental chamber studies to quantify the contribution of this. So I always think that, like we should make sure that the fundamental people are integrated into, future few campaign plannings. That would be wonderful. And of course, I thank all the collaborators of SOAS. And this picture is a little out of date, but this is the core people who are involved in all the work I talk about. So Chris is a fourth-year student, so he did the chamber experiments. And Lusu is my first-year student. He's about to graduate, and he did all the ambient measurements throughout the Southeast US, and he built the chamber with me. And Theo is the postdoc, and she worked on the night-to-day transition. And I thank NSF and EPA for funding, and thank you for your attention.
Thank you, Sally, for a really, really nice talk. We have a little bit time for questions. Please use the microphone.
My question is about the difference between alpha-pinene NOx product and the beta-pinene NOx product, and why you feel the difference is that the big transition you can see the night and day, or the light and the dark, and the alpha-pinene one goes away and the beta doesn't.
Yep. So yeah, so this is actually, a great question. Like when we got this data, that's the first question we asked, is like, why these organic nitrates behave very differently? And so we go back to look at the literature of some of the photolysis of the organic nitrate papers. So it seems that there are some studies which shows that if the organic nitrate has a carbonyl group close to the organic nitrate, versus the carbonyl group is farther away from the organic nitrate, that will actually affect the rate of photolysis. And maybe could be one of the reasons. And so one of the things that we would like to do more is to try to understand maybe the functional groups of these organic nitrate. With the SIMS measurement, we get a formula. You got the C10, H something, O something, but we don't really know much about whether it's a carbonyl group, where it is relative to the organic nitrate. And it seems where it is actually matters in terms of the photolysis rate. And of course, and another thing is that these experiments with photolysis and OH oxidation together. Like we have both processes happening. So our next step is to try to isolate the photolysis and the OH oxidation and see if we can learn more about these two different behaviors.
Thanks.
Sally, I was just curious whether you know what the pH is in the chamber and whether it's similar to the pH estimate for ambient aerosol for the Southeast US.
Yeah, so basically, come back when we were designing the chamber experiments, we were trying to make it Southeast US relevant, and based on Rodney Weber's measurement and Sano's isopropia calculation, the pH is about 1, right? And so we actually make this really acidic seed by mixing magnesium sulfate and sulfuric acid, and we use the same calculation, and we get to pH about 1. So we make sure that it is a lot of aqueous water because it's high humidity, and the pH is also low, just to simulate and make sure that we have the same type of environment in the chamber compared to the ambient.
We'll just keep going down the line here. So, Sally, I want to take you back a few years to your graduate work. You did some nice work on NO3+ isoprene then, and you showed, at least in your experiment, some quite large yields for organic aerosol from the NO3+ isoprene reaction. I'm wondering if in your more recent fieldwork you see any markers that are characteristic of that, or if you can speculate at all on what the organic aerosol source is in your estimate from any of the work that you've done from the isoprene reaction.
Yeah, so the isoprene NO3 reaction definitely happens at night, like based on that little calculation we did, it's like maybe 30-something%. But maybe majority of this will be more in the gas phase than the particle phase, relatively, compared to these monoterpenes. And like Joel Thornton's group measured all these speciated organic nitrates at SOAS, and they did see a lot of organic nitrates that is a C5 formula, which they propose that is from isoprene organic nitrates. And the perpetuate question is, how much is in the gas phase? How much is in the particle phase for both isoprene nitrate and monoterpene nitrate? And that comes back to the question we got to maybe standardize our compounds and try to calibrate our instruments, because we measure all these peaks, but we don't really have much idea of how much there is. Yeah, but I would say in general, probably it's correct to assume most of the, or more of the isoprene, organic nitrates will be in the gas phase. And Paul Winberg's group have done a lot of follow-up studies on the fate of these isoprene organic nitrates.
All right, so I'm going to press you a little harder then. What do you know of a specific marker in the AMS spectra that would help you identify the isoprene nitrates?
So, well, one thing maybe, I don't think there is a definite way, but there might be some hope. So if you remember from one of my slides, that's my organic nitrate estimate. Yeah, this one. So AMS, the good thing about organic nitrate or inorganic nitrate fragmentation in the AMS is that they look quite a bit different between organic and inorganic, and maybe also different classes of organic. So this is something I would love to pursue more. So I'm just going to use this. So you see that the NO-NO2 ratio for ammonium nitrate is about 2, right? And at first, we thought that maybe the NO-NO2 ratio for isoprene nitrate and monoterpene nitrate would be different. If that is the case, then we might potentially be able to do some source apportionment based on this NO-NO2 ratio. And it turned out to be not as simple as that. So most of the literature measuring NO-NO2 ratio in AMS for isoprene particulate nitrate is about 5. And in general, I did not have it here, monoterpene nitrate is more 10. But when we did experiments under different conditions, we actually saw NO-NO2 ratio for monoterpenes also close to 5. So that kind of make it very challenging to, like, at first, I was like, the first couple of set of experiments we did is like, oh, that's great. Isoprene organic nitrate is about 5, monoterpene is about 10. But I think there's more studies that needs to be done to kind of map out that landscape. But maybe there's some potential hope in there. But it's very hard to tell just based on these 2 fragments.
So at the beginning of your talk, you linked the low oxidation OOA to the nitrate and monoterpene oxidation. I was just wondering if you had any opinion about what you think drives the loss of that, because you kind of showed that these nitrates that you form are kind of resistant to the temperature increases and to dilution. Do you think it's mostly deposition that drives that diurnal cycle, or is it oxidation to more oxidized products in the
Yeah, so that is a wonderful question. I've been thinking about this for a long time. I don't know the answer yet. But so what we see is that we did experiments with alpha-pinene, beta-pinene, and nine-malene. And they all show very different behaviors, right? And the question is, and then bring in the question of alpha-pinene organic nitrate. So how much of those, like, they did see the ambient, so the total nitrate is kind of like this, right? It goes down during the day, but that is a sum of all the potential species that you sum up monoterpene, different types of monoterpene, different types of isoprene. So I think we actually need more. I mean, this is kind of the beginning of all these studies, and we are learning that the different VOCs make different type of organic nitrates that behave differently. So I think we need to continue to do more experiments, maybe with different VOCs, or try to understand how to link these observations to their particular structures. And maybe now we can try to sum everything together. But as for now, I don't really know why we're seeing this. And like the beta-pinene is resilient, but maybe nine-malene actually contribute to a lot of that ambient nitrate.
All right, if there is no more questions, let's thank the speaker again.